All right, this is AP Calculus AB Section B, Unit 3, Lesson 4, Other Integration Techniques. As the name suggests, this lesson is about a number of different techniques that can be used. Several of them involve algebraic manipulation or trigonometric identity manipulation to change the integrand to a different form. And so, without further ado, let's go ahead and walk through the examples. These are examples that you will work later on in the lesson. So if you want to watch these videos after you do the lesson, that's perfectly fine. All right, so here we go. Number one. So we're going to find the integral, definite integral from 1 to 2 of 1 over x plus 4 minus 1 over 4 all over x. The key here is almost should be fairly obvious. When you have a complex fraction, complex rational expression, you can eliminate the rational expression. You can multiply top and bottom by the least common multiple, 4 and x plus 4. That's one technique. In this particular case, I prefer to just do the subtraction. Kind of crisscross applesauce. So this becomes 4 minus x plus 4 quantity, so minus the quantity x plus 4 is minus x minus 4, all over x plus 4 times 4 times x. So 4 times x plus 4. Okay, so the integral from 1 to 2. Okay, and 4 minus 4 is 0, so this and the x's then cancel. And so we're left with 1/4. I'm just going to pull the fraction out front. 1/4. The quantity 1 over x plus 4. Okay, we could use u substitution at this point with x plus 4, but du is 1 dx. So it's really not necessary. The integral of 1 over x is ln x. So this is 1/4 ln of x plus 4 absolute value plus c. Oh, not plus c because this is a definite integral. So we're going to do it from 1 to 2. Oh, and I think we ended up, oh, there's a negative in front here too. So there's a negative pulled out. Negative x. Good thing we caught that. So negative 1/4. Okay, so definite integral from 1 to 2. Let's plug in 2. So equals negative 1/4. Negative 1/4 ln 2 plus 4 ln 6 minus ln 1 plus 4 ln 5. Okay. Now, if you distribute the negative, this is 1/4 ln 5 minus ln 6. And if you use the quotient rule for logarithms, this is 1/4 ln 5/6. Okay. And that is it. So negative 1/4 ln 5/6. Which is the same as negative 1/4 ln 6/5. Okay, so that's number one. That's the first example I'm going to work. Second one. Okay. Second one. So we have the integral of 4x plus 1 over 4x squared plus 2x plus 3 dx. Okay. Now I might be tempted to think, well, maybe this'll factor. Actually, whoops. This is a previous example I did. I read the wrong one. This was a u substitution one. Okay. Now, what I want to do is x to the 4th minus 3x squared plus minus 1. X to the 4th minus 3x squared minus 1 over x plus 2. Okay, dx. Now the first thing I notice here is, well, if I want to try U substitution, the derivative of fourth order is a third order, so the U substitution is not going to work. I might consider factoring, but there's no factor in the numerator that's going to end up with a 2x plus 2, so no canceling there. And so that leaves us with long division. Now we could do long division, x plus 2 divided by. Remember, we need to write every power of x. There are no x to the thirds. There's negative 3x squareds. There are no x's, and there's negative 1, and we can do long division that way. And I think that's the way the lesson did it. This happens to be division by a factor that's x plus or x minus a. And we can use synthetic division in this case. If you recall synthetic division, we use the opposite because it's x minus a, and write the coefficients. 1x to the fourth, 0x cubed, negative 3x squared, 0 x's, and negative 1 constant. Okay, bring down, multiply, negative 2, add, negative 2, multiply, 4, add, 1, multiply, negative 2, add, negative 2, multiply, 4, add, 3. So this comes out as the integral of 1 x to the 0, 1, 2, 3, x to the third. So x to the third minus 2x squared plus 1x minus 2. And then 3 is the remainder, so we say plus 3 over x plus 2 dx. Okay, and now it becomes one that we can work fairly straightforward. The integral of x cubed is x to the fourth over 4, or 1/4 x to the fourth. The integral of x squared is x cubed over 3, so minus 2/3 x cubed. The integral of x is x squared over 2, or plus 1/2 x squared. The integral of negative 2 is negative 2x. And the integral of 3 over x plus 2 is the natural log, 3 times the natural log of x plus 2 plus c. Okay? All right, so there we go. That's number 2. All right, number 3. Número 3. Okay, number 3. Number 3 is the integral of x minus 1 square root x squared minus 2x all under 1 dx. Now what catches my eye about this one is it's similar to, or reminds me of, a derivative of one of the inverse trig functions. You may recall the derivative of secant, arc secant of x is this. It is 1 over absolute value x square root 1 minus x squared. Okay, and that's what I'm working off of here. So it's a term with x in it multiplied by a square root. So that suggests that maybe changing the form here of the square root part. So here's what I'm going to do. I'm going to say x minus 1 square root, and I'm going to complete the square. X squared minus 2x. Now 1 plus 1 is 2, so 1 times 1 is 1. So that's what I add. But I can't just willy-nilly go adding 1 without also subtracting 1, because I don't want to actually change the value. Okay, so there we go. So we add 1 and subtract 1. Now this part is a perfect square, right? It's a perfect square. So this is x squared minus, or x minus 1 squared. So let's rewrite this here. X minus 1 square root x minus 1 squared minus 1 by completing the square. Don't forget the dx. Integral dx. Okay, now we're almost there. Now, the square root here has to be positive, and it only works where this is positive anyway. Okay. And actually, I just realized I had this backwards. It's x squared minus 1. Let me remind myself here. I'm going to pause the video. Yep, I was right. I was wrong in the first place. It's at root x squared minus 1. Okay, so that's going to help because otherwise it wasn't going to work. So let's see what this equals here. So now I can use u substitution. Let u equal x minus 1, right? And this becomes the integral of u square root u squared minus 1 under 1 du. Du equal, because since the derivative of x minus 1 is 1 dx, du equals dx. Okay? And so this is simply arcsecant. So arcsecant of u, but u is x minus 1 plus c. And there we have it. All right, so that's number 3. Got two more. Let's see how quickly I can get this done without taking too long. It's tough when there's so many different ideas, and this even isn't cumulative. All right, so number 4, the middle quattro. Okay, find the indefinite integral of sine 2x over cosine x. Okay, now you may recall dx. You may recall the double angle identity. If you don't recall the double angle identity, then you may recall the sine addition formula. Sine of a plus b is sine a cosine b plus sine b cosine a. Now in this case, this is sine x plus x. So this is sine x cosine x plus sine x cosine x, or simplified 2 sine x cosine x. Okay, and that is the double angle identity. Sine 2x is 2 sine x cosine x. So you may recall the double angle identity, or you may have to work it out from the sign for angle addition. All right, but this is the integral of 2 sine x cosine x over cosine x dx. And we have a little bit of cancellation. Now remember one thing. This means cosine x cannot equal 0. X cannot equal pi over 2 plus any multiple of pi. Okay, so equals the integral of 2 sine x dx, and the integral of sine is negative cosine, so negative 2 cosine x plus c. Okay, all right. Yep. And finally, the last one. This is kind of a weird place to put it, but I'm guessing they weren't quite sure where to put this. They didn't want to have a complete lesson. It's called L'Hopital's rule. It looks like El Hospital, right? El Hopital. L'Hopital's rule. And it really has to do with finding limits. Okay? If you take a limit as x approaches anything, a, right? And of a of x over b of x. And a of x goes to 0, and b of x goes to 0. Then, if that is the case, then the limit of x as x approaches a is equal to the limit as x approaches a of a prime of x over b prime of x. Now it can also be shown numerically or symbolically that this is true if the limit is infinity over infinity as well. All you got to do is divide by the top and the bottom to turn it into a fraction, and you can turn it into a fraction where so let me show you. A of x over b of x. If I divide by a of x, or divide by a of x, b of x, and divide by a of x, b of x, okay. This is the a of x cancels, and we have 1 over b of x, and 1 over a of x, 1 over a of x, but b of x is going to infinity, so 1 over b of x is going to 0. A of x is going to infinity, so 1 over a of x is going to 0. So in other words, L'Hopital's rule works whether it's the top and bottom are both going to 0 or going to infinity. Okay, all right. And it doesn't matter what we go to, just so that the limit is 0. So let's use that rule to find this limit, number 5. We're going to take the limit as x approaches 0 of sine 2x over cosine 3x. Or not over, yeah, sorry, sine 2x over sine 3x. Okay, so let's check it. As x approaches 0, this approaches 2 times 0, or approaches 0, and sine of 0 is 0. 3 times 0 is 0, sine of 0 is 0. So this is going to 0 over 0, which is undefined, right? Well, we don't care what the value is at 0. We care what it is as it approaches 0. So we take the limit, this is according to L'Hopital's rule, we take the derivative of top and bottom. Derivative of sine is cosine 2x. Use the chain rule, the derivative of 2x is 2. The derivative of sine is cosine 3x. The derivative of 3x is 3. Now check it out. So as x goes to 0, 2x goes to 0, cosine of 0 is 1. The top becomes 2. X goes to 0, 3x goes to 0, cosine of 0 is 1. The bottom goes to 3. So the limit is 2/3. All right, so hopefully that helps. I know that was a little long because I did a lot of problems.